Okay, hello everyone. My name is Michael. I'm the CTO of NuCypher. And what we do is pretty much a decentralized key management system. So like imagine something like a hardware security module, but instead of being a hardware, it's actually a decentralized network. And of course, this decentralized network cannot decrypt any of your data. And let me tell why are we doing that and how actually it works. So imagine some use cases like Daniel was explaining earlier today about sharing, let's say sharing files or sharing chunks in Swarm or something like that. How would you normally do that using traditional cryptography? I mean, a naive way would be, let's say you want to share data with multiple recipients, right? That's the goal. Naively, you would encrypt data with public key of every recipient and store, you know, however many copies, like whatever number of recipients you have, that number of copies of the data. That's not efficient, of course, and you can do better, and that's exactly, I guess, what's happening in a Swarm. You encrypt only the symmetric keys, or like the root symmetric key with the public key of each recipient, and store that in the ACL list. But the disadvantage is of course, that if you want forward secrecy, you need to change the key every time, and every time you do the write, you need to basically have an overhead of changing the ACL for all of your recipients. So if you have 10,000 recipients, that would be a problem, I guess. And of course, you could opt in for a centralized solution, but that's kind of not what we're doing here. Another example would be, well, probably more relevant with tens of thousands of people is end-to-end encrypted group chats. So you can do the same kind of thing for each message. And well, if you want to be able to revoke access to your chat, then you would need to change your symmetric key with every message. And with traditional cryptography, you would need to overwrite your symmetric key encrypted with public key of every recipient every time, which is, again, not optimal, not scalable. Or it's the same with distributing video. So if you, I'm not talking about transcoding, I'm talking about only CDN here. So if you want to have kind of conditional delivery of encrypted video content, you kind of face the same scalability problem. You pretty much, if you split your video into chunks, and each chunk you encrypt with this individual symmetric key, you pretty much would need to encrypt it, all symmetric key for it for every recipient every time, which is, again, not ideal, and also it actually would, when you add or remove a new recipient, you would need the owner of the data to stay online to kind of grant and to be granting and revoking access every time. Anyway, so of course, an easy way to solve it would be to use a centralized solution. That's what all the centralized services are doing today, and this has its own problems with eavesdroppers and some guys. So probably don't want to do that. So what do we do? What we do, we combine something called proxy re-encryption with decentralization. And since proxy re-encryption is not a well-known concept, I probably should explain it first. So essentially what proxy re-encryption is a set of encryption algorithms which, apart from encrypting and decrypting, they also allow transforming texts or ciphertexts from being encrypted under one key to be encrypted under other key. So imagine this. You have Alice and Bob, and Alice originally didn't know which Bob she wants to share data with. So she encrypted data for herself with her own public key and stored somewhere. And later on, let's say Bob came and said, oh, well, Alice, hey, can you share your data with me? And she said, sure. So how does she do that? She takes Bob's public key, her own private key, and calculates something called re-encryption key. And then she can give this re-encryption key to the proxy. to some third-party service, which only responsibility is to transform the ciphertexts from Alice's to Bob's. Proxy, who has this re-encryption key, cannot do anything else, only to transform data. It cannot decrypt the data. What's even more important, Alice can continue publishing updates to this data. Let's say adding new files encrypted with exactly the same with her public key. And Proxy still will be able to transform this data, this new data, to Bob. Well, of course, until Alice asks Proxy to remove this re-encryption key. And, well, that's the encryption primitive we use. So let me first explain how we use that using one proxy, and then how we decentralize that. So, well, imagine you use just a typical scheme you use for encrypting files. So you encrypt your file with a random symmetric key, and you encrypt symmetric key with the public key of their sender, let's say Alice. So this is your encrypted ciphertext, like text encrypted with a block cipher, and encrypted symmetric key. And you store that in some storage layer, whatever that is. And now, let's say the sender grants access to the receiver. How it works? The sender takes the receiver's public key and calculates the re-encryption key from the sender's private key and the receiver's public key. And now, let's say, what happens when the receiver reads the data? The receiver fetches the data which was encrypted for the sender, and the receiver sees that the receiver cannot decrypt it. So what does he do? He takes this encrypted symmetric key and sends it to the proxy, asking it to re-encrypt. Proxy takes this re-encryption key and transforms encrypted symmetric key, which was encrypted for Alice, into being encrypted for Bob. In this, at this moment, Proxy did not see anything except for the two ciphertexts, like ciphertext in, ciphertext out. And then using this encrypted, well, Bob can already decrypt this transformed encrypted symmetric key. He does that, he gets the symmetric key, and using that, he decrypts the data. So Bob sees the data. So that's just what you get using normal proxy re-encryption. But then, let's say if we run such a service, there is a problem. What happens if proxy, for some reason, refuses to process the data? Maybe some collusion happened. I don't know, some nation state interacted with the hoster of the proxy and said, oh, hey, we don't want this guy to decrypt data. Let's ban him. And then this proxy refuses to work, and, well, proxy doesn't read the data, but it can refuse to work. And we kind of, I think that would happen in Russia today. Anyway, so how do we prevent that? Well, we try to decentralize things. And for that, we actually designed something called, something which you would call threshold proxy re-encryption scheme. We call this one Umbrel. And what it does, you basically require M out of N proxies to re-encrypt data for Bob to be able to decrypt it. So let's say Alice creates N re-encryption keys, sends to N proxies, and if only M proxies re-encrypt data, then Bob can combine those ciphertexts and then get something which he can decrypt. And that's, so this is that's what the encryption scheme we use. It's a public key encryption scheme. Well, for public key encryption, it's actually using ECIS. So it's, well, ECIS with bells and whistles. ECIS on the same curve as Ethereum uses, SecP 256K1. And For the block cipher, we're using SHA-20. Well, we're actually quite agnostic to the block cipher. It can be anything. We actually, originally, we made it for EC El-Gamal, but EC El-Gamal has this problem that it's only CPA secure, and we are kind of more secure than that. It's, this scheme has CCA security. But you know, it can be done for EC El-Gamal also. Also, an interesting thing is that what happens if the proxy misbehaves? What happens if the proxy returns garbage instead of re-encryption and says, oh, I re-encrypted correctly, trust me. We implemented something which allows us to prove that the proxy re-encrypted correctly using zero-knowledge proofs. And if the proxy does not re-encrypt correctly, Bob can present evidence to the whole network, and the proxy can be punished, slashed, and stuff like that. So that's our like encryption scheme is on GitHub in PyUmbrel repository in like NuCypher's GitHub, and also there is a formal specification in Umbrel doc repository on our GitHub. And I guess let me show how you would, well, the network itself, the kind of decentralized network as a proxy re-encryption service is not up yet, but you can play with mocknet, and it basically, let me show how it looks like. So, well, it's like right now it's reference implementation, so it's in Python, although the speed is like Python overhead is actually pretty tiny compared to how elliptic curve cryptography is. So, well, you basically first import all the things, and you obviously start from generating keys for like private and public key pairs for Alice and Bob. And okay, let's see what's next. Oh yeah, well, you instantiate the mocknet, like what is kind of mocking the real network which will be there. And let's say Alice encrypts some data for herself. So the ciphertext, and you get ciphertext and capsule. Ciphertext is the text, plain text encrypted by the symmetric key, and capsule is pretty much encrypted symmetric key. It's not quite that, but it's actually pretty close. So you can think of it as that. And okay, then Alice produces the re-encryption keys, which she sends to a bunch of proxies. And you use split re-key method and produce something which we call k-frags. So you generate 20 k-frags, and then grant permission, basically upload these re-encryption keys to their proxies selected in a certain way. And then, well, Bob asks, or Bob, let's say, takes the, downloads the data, the encrypted data which Alice produced, and the capsule, the encrypted symmetric key. So Bob asks the proxy network to re-encrypt the capsule, and then I guess he can decrypt the data. Well, I guess he needs to reconstruct the actual, like, the capsule he can decrypt, and then decrypt the actual data. So the actual decrypted data is like clear. On the other hand, if Alice revokes the access, the re-encryption keys are removed on the proxy side, and Bob, I guess Bob cannot decrypt the data anymore. So that's how the network approximately will work, and we are actually getting very, very close to real testnet, which will happen probably by the end of this month. And yeah, I didn't touch how we use token economics to incentivize proxies to operate fairly. Basically, the function of the token here is not to pay for services. You pay for services using ethers. The function of the proxy is kind of the amount of trust you put into each proxy. So however many coins proxy holds, this is the this is proportional to the amount of work which proxy will handle. So our token is kind of ASICs for these proxies. Why wouldn't we use ethers for that? Like, in principle, you could lock ethers and do that, right? And basically distribute trust proportional to amount of ethers. If you did that, then this kind of attack would be possible to happen. Imagine someone acquired a lot of ethers, like, well, I don't know, bought ethers in like on credit, right? And put that ethers as a stake, and then acquired more than 50% of the network, compromised the network. The network value went to 0, but the guy who compromised it didn't suffer because he used ethers to stake, and the ether value didn't drop. So that's why you cannot use ethers for staking, and you need to use actually you need to use actual like NuCypher tokens. So it's important that the value of the token goes to 0 if you compromise the network. So it's very expensive to actually attack the network. Well, also when you put out tokens and produce the work, well, this also produces the new coins according to inflation schedule, and also the node gets slashed if it's caught in misbehavior. That's why we needed to include these proofs of misbehavior into proxy re-encryption algorithm. And mining rewards, well, I guess instead of this, I'll probably just show this. The reward rate is exponentially decreasing, and if you commit to staking, if you commit to holding policies for a long time, your reward rate is higher. So this kind of commitment time is how long can you grant access for. Like if the access grant time is more than the amount you commit for staking, then you actually cannot process it. So, and we basically have it so that, well, at least the current thought is that 1 year of staking is probably 2 times the rewards of short time staking. Interestingly, if you you can cash out the rewards, or you can restake it, and if you restake it, apparently what you get after years will be much larger. So who are the users, the kind of future users for our network when it's up? Well, interestingly enough, a very, very large proportion of companies are actually medical data companies. So actually one of them is here in Ljubljana, IRO network, but there are kind of a bunch of others. And also, it's pretty useful for decentralized marketplaces and different sorts of things. I guess one of the guys from Fluence is here to use this proxy re-encryption network to share data in their Fluence database. And yeah. So yeah, this is basically what we're up to. And please, if you want to check this out, please go to our GitHub, play with the mocknet on GitHub, or you can find the PyUmbral in proxy re-encryption algorithm. And yeah, or feel free to jump on our Discord or write an email. Thank you.